Hello, I'd like to give our first installment of the office hour equivalents for Unit 1, Module 1. These are all questions that came up during office hours. These are Tuesday, Thursdays from 2 to 3:30, and on Fridays from 11 to 12. All these times are available in D2L. So the first question is about the signs of different phase changes with respect to energy. And so when we look at this particular representation of the different phase changes, what we're going to see is in red, all the processes in red require energy, and the delta E is positive. All of the processes that are in blue are negative and negative delta E, and they correspond to release of energy. So in red, we have melting, which is the transition from solid to liquid. We have liquid to gas, which is vaporization, also known as boiling. We have solid to gas, much less commonly known, and that's called sublimation, which is the direct transition from solid to gas. And all of these processes require energy with delta E as positive. In blue, we have the reverse phase transition, which is instead of solid to liquid for melting, we have liquid to solid, which is called freezing. This releases energy. We have gas to liquid, which is condensation. This also releases energy, delta E negative. And then gas to solid, the opposite of sublimation, is called deposition. So the delta E positive requires energy, so it's a positive delta E. And the release of energy is the blue, or delta E is negative. Please keep in mind that all of these processes happen at a single temperature, and so the temperature does not change during any of these processes. The reason why we have this type of requiring energy and releasing energy is due to the energy ordering. If we go from something that's lower in energy up to something that's higher in energy, that requires energy. So solid to liquid is going to higher energy, liquid to gas is going to higher energy. So the most stable phase is solid, the least stable phase is gas. And so we require energy to go up to less stable phases, and then energy is released if we go from less stable to more stable. And that's a general rule in chemistry, is that if something is going from less stable, higher energy to lower energy, it releases energy. If you're going from something more stable up to something less stable, then that requires energy. All right, so the next question is about making sure you feel comfortable about the phase diagram, what it's telling you. So here in region 1, we have the solid phase. This is going to be at high pressures, low temperatures. High pressures and low temperatures for the solid. Gases are always going to be on the bottom right, which are high temperatures on the x-axis, high temperatures, and low pressures. So using that, we would assign region 1 is solid, region 2 is liquid, and region 3 is gas. The phase transitions that match, so let's take a look. So 1 to 2 is going from solid to liquid, that's called melting. 1 to 3 is going from solid to gas, that is sublimation. And for this process, okay, so solid to liquid melting is delta E is positive. From going from solid to gas, delta E is positive because both of those go from a solid, which is the most stable, up to a more unstable phase, so those delta E's are positive. Going from 3 to 1, the opposite of sublimation, this would be gas to solid. This is called deposition, and in there we would delta E is negative because we're going the opposite. We're going from high energy or low stability down to the most stable phase, solid, so that's going to release energy. Okay, so now we're going to get some quantitative information from the phase diagram. So determination of the freezing and boiling point at 10 atmospheres. Well, the first thing we do is that we identify 10 atmospheres. So where's 10 atmospheres? It's here. So now we draw a line, a horizontal line, and where it intersects the solid liquid line, that is where melting is going to occur. Where the line intersects the liquid gas interface, that is where boiling is going to occur, or vaporization. So we drop a line down from the solid liquid intersection, drop it down, and we would assign that temperature to be about minus 50 degrees Celsius. For the boiling point, we do the same thing. Where 10 atmospheres intersects that line, which is the boiling point line, we go down, we see that, and we assign that, let's say, minus 10 degrees Celsius. So these points, the freezing and boiling point, these are phase transitions. They must be on the solid line, right? The solid black line here is the interface between the two phases. That's where the phase change occurs. So the freezing temperature is minus 50 degrees Celsius and the melting temperature is minus 50 degrees Celsius. Remember, this is just about what direction you're going. Are you going from liquid to solid? That's freezing. Going to solid to liquid, that's melting. Same is true for vaporization and condensation. That's what we call boiling. And so minus 10 degrees is the temperature for vaporization. Minus 10 degrees is the temperature for condensation. Both of these are associated with the boiling point, right? So the intersection of the liquid and gas at a given pressure. It's really important that you feel comfortable obtaining these numbers from the solid lines on the phase diagram. Okay, so now we have we're given a certain pressure and temperature, and we're asked what would happen, what phase change would occur if we decreased pressure. So we look at, well, where is 72 atmospheres in 0 degrees Celsius? So we go over to, we're at 72, we drop down, okay, 0 degrees Celsius. So we're right at this point. We're in the liquid phase at 72 degrees and 72 atmospheres, and 0 degrees Celsius, we are in the liquid phase. Liquid. And now, as we reduce pressure, lower pressure, and go down this line, we would then go from liquid to gas phase. This is vaporization, or the phenomenon known as boiling. So we would expect vaporization or boiling to occur as we start at 72 atmospheres and 0 degrees Celsius. Keep the temperature constant and slowly lower the pressure. Okay, so in this particular problem, we're asked to find the normal melting point of this particular compound. So let's go through and fill out some information. So what does normal mean? Well, normal means the pressure at 1 atmosphere. So we draw a dashed line from 1 atmosphere across. So we identify the phases, solid, liquid, gas. And so where the solid-liquid interface is at 1 atmosphere, we look at the temperature that occurs and we look for boiling. We look at the liquid gas interface at 1 atmosphere. Using this information, T melting at 1 atmosphere occurs at 250 Kelvin. If we wanted to calculate the degrees Celsius from that, we would take the Kelvin temperature, subtract 273 degrees, and get the degrees Celsius. And that would be the answer, minus 20. For boiling, it wasn't asked, but we can calculate that too. And at 1 atmosphere, that temperature would be about 380 Kelvin, or if we subtract 273 from it to get the degrees Celsius, we get 107 degrees Celsius. So one thing is you want to make sure you can navigate across a phase diagram, and two, that you can convert between Kelvin and Celsius. And remember, normal will be asked on the test, and it's the pressure at 1 atmosphere. Now we have some more work with heating and cooling curves, and so if you'd like to see these problems worked out, we have the next 4 slides go through them in great detail. Okay, so we're at the triple point, meaning that the solid line below here must be the solid gas interface. So if we're going from A to B, we are heating solid. At B, we are subliming, meaning solid to gas. And then B to C, we are heating the gas. You want to make sure that you can identify these 3 individual processes, because this will help you identify the correct drawing that you have to pick in terms of the change in energy with temperature. The next thing we want to do is we want to assign the delta E for each of these processes. So delta E is positive as you heat a solid. It's positive as you go from solid, the most stable phase, up to the least stable phase. So that requires energy. So delta E is positive. And then heating the gas, anytime you heat, the delta E is positive. So you have 3 separate, distinct positive processes. So that whenever you're heating, that looks like a ramp. So all of these share the ramp up. Well, B and D share the ramp up in the phase change from in sublimation, going from solid to gas. That's shown as a step, and then a ramp as you heat the gas. So we expect to find an image that is ramp, so we're starting at the initial temperature of TA. We expect to see a ramp, a step, and then a ramp. That should be what we would see from A to C, and that corresponds to answer B. First, we're heating the solid. Delta E is positive. Then we sublime at a given temperature, so that's a step up with delta E positive. And then we heat the gas, which is a ramp of delta E positive. Answer B. So now we have the opposite process. We're starting at C and going to A. So that means we are from C to B. We're going to be cooling the gas. That's going to be delta E is negative as we cool. At point B, we're going to deposit gas particles into the solid phase. That's delta E is negative. And then from B to A, we're going to cool the solid. That's also delta E is negative. So we need 3 separate processes. We have to make sure that we have to, since we're talking about negative numbers, we have to plot versus delta E. We want to make sure we have an axis for delta E that's negative. We put our 3 temperatures, and in this case, we're starting at point C. So that means delta E is 0 at point C. Cooling is minus. So there's our delta E at 0 at TC. That's where we start. And wherever you start, whatever temperature you start at, you put that value at 0 at whatever temperature you start at. So then we cool the gas, then we deposit at the deposition temperature, and then we cool the solid. All of these are negative values, so first cooling the gas, the step at a given temperature, the deposition, and then cooling the solid. This graph then would appear as B. So whenever there's a phase change, we definitely need a step. If it's going from high energy, like gas, down to solid, then the delta E has to be negative, and it's going to happen as a step down. Okay. So let's look at a more complete analysis. That was the solid gas interface. But what if we have the case where we're at 200 Kelvin and 1 atmosphere, and we want to look at the heating and cooling curves of going to point B, which is at 1 atmosphere but 450 kelvins. So going from A to B is traveling from solid to liquid to gas. All right, so that's going from 200 Kelvin all the way to 450 Kelvin. So what are the individual processes? Well, first, from 200 to 250, we're heating the solid. And at 250, we're melting. So we're going from solid to liquid. From 250 to about 380, we're heating the liquid. And exactly at 380, we start to boil or vaporize liquid to gas. And then from 380 to 450, we are heating the gas. So 5 different processes, all of them with delta E positive. So let's put our temperature versus time picture up. Okay, so here it is, and we're going to put our temperatures on this graph, 250, 380, 450. So the first thing that happens is we heat the solid, so that's shown as a ramp. And then at the melting temperature, the temperature is going to remain flat for some time as we melt the solid. And then we're going to heat the liquid up, and then we're going to boil, which is going to be at the same temperatures. We're going to spend some time at the temperature of boiling or vaporization, and then we will heat the gas. Right? So this would be the 5 different processes. Every time you heat, you have a ramp, right? Because it's a one-phase system, so you're just changing the temperature. And then at the phase changes, you have flat behavior because the phase change occurs at a single temperature. The delta E versus temperature is slightly different. So we put the temperature now on the x-axis. And since we're heating, everything's positive. So from 200 to 250, we have a positive ramp. And then we have the phase change, which is a step. And we have heating the liquid up to 380. A step as we change from liquid to gas, vaporize, and then heating the gas. So if we were to put all the steps in there, heating the solid, melting is the step at the melting temperature. Heating the liquid occurs as a ramp. Vaporizing at the boiling temperature, at a single temperature, there's a big step as we go from liquid, low energy, up to gas, higher energy. So that's a delta E positive. And then we have the heating of the gas. So those are all of the steps. There's 5 steps. This is how you construct the temperature versus time and the delta E versus temperature for information given on a phase diagram as we go from A to B. The next slide will be going from B to A. All right, so same curve. We now put our points B and A. Now we're going to be going in this direction, which is cooling. So we're going to start off at 400 Kelvin, B hot, right, or 450 Kelvin hot and B, and then cool all the way down to 200 Kelvin. So we do the same thing. We break these into steps. First, we're going to cool the gas from 450 Kelvin to 380. And then we're going to, all right, so that, and then it's going to condense the gas into the liquid form at 380. Then from 380 to 250, we will cool the liquid. And at 250, we will then freeze the liquid into solid. And then from 250 to 200, we will cool the solid. So 5 different steps. And then we're going to make the same 2 graphs. So temperature versus time, 200, 250, 380, 450. And so the first thing that happens is we cool the gas. So we go from 450 to 380. Then the temperature remains constant as we condense gas to liquid. Then we cool the liquid. And then at 250, we freeze the liquid into solid. So that's a phase change. So the temperature is flat at 250. And then we cool the solid down to 200. So cooling the gas, condensing the gas to liquid, constant temperature, cooling the liquid, temperature changes, freezing at the freezing point, which is constant, and then cooling the solid from 250 to 200. So those are the 5 steps, and that's how we would show it as temperature versus time. If we make the plot of delta E versus T, since we're cooling, we have to include the negative axis. We're going to put our temperatures up, 450, 380, 250, and 200. We're starting at 450 Kelvin, so we put our delta E of 0 right at the starting temperature at 450. We're going to cool. So delta E is going to go down. So all these processes are going to release energy, so it's going to be negative. So delta E goes from 450 to 380, cooling the gas. There's a big step down. Then there's the cooling of the liquid. There's another step down as we freeze. And then there's a cooling of the solid. So we should see the cooling of the gas, the step of the phase change going from gas to liquid, the cooling of the liquid, the phase change of the freeze of liquid to solid, that should be another step at the freezing point, and then cooling of the solid as a ramp. So all the delta E, all the processes here, the 5 individual steps are all negative. The ramps are the cooling of the phase, while the steps are the phase changes. All right, so the last slide is the last topic we covered, which is looking at vapor pressure curves when 2 or more substances are shown on the exact same graph. So here we have a vapor pressure curve, meaning that we're just looking at pressure and temperature and the liquid-gas interface. The normal boiling points for water and C2CL4 can be read off the graph, so we look at that. So water should boil here at 370. The C2CL4 is going to boil at about 390. We can also identify 3 different regions based on the 2 curves given. So first, the boiling point of water is recorded as 373. It's the most volatile and has the highest vapor pressure because it has the lowest boiling point. Because when we look at the boiling point of C2CL4, its boiling point is 390. That higher boiling point means that it must be less volatile than water, and it has a lower vapor pressure than water. In the different regions, this is really important, especially in terms of separations. So we're going to look at phase A, phase of water, and phase of the C2Cl. Well, that should be Cl4. Okay, so in region 1, we see that using our guide that we talked about in class, if the region is above the line for a particular substance, that substance will be in the liquid form. If we're below the line, then we would be in the gas form. Okay, so let's see what that means. In region 1, water is a liquid because region 1 is to the left above the line, the dashed line for water. It's also above the solid line for C2CL4, so they are both liquids in region 1. In region 2, now region 2 is to the right or below H2O, and so water is a gas, but it's still above the line for C2CL4, so it's a liquid. And in region 3, we are to the right or below both of the lines, and that gives us both gas for both water, H2O, and C2Cl4. So based on the question asked, they're asking about region 1. They want to know in what conditions would we expect there to be liquids, both present at 1 atmosphere. And then we look and we see, well, that's any temperature below 373. That's where region 1 starts at 1 atmosphere. So we could also identify in the answers different regions here. So region 3 starts at above 393 Kelvin. Region 1 is below 373 Kelvin. And then region 2 is between 373 and 393. This particular region is very interesting in terms of separation. So I just highlighted it there between the two lines. That's because we can separate water and C2Cl4 under these conditions by vaporizing water and leaving behind the C2Cl4 liquid. This is done usually through distillation, and as we talked about in the moonshine problem, this allows us, so you can always capture the lower temperature boiler by distillation, by putting in the gas phase and then collecting it in another vessel that's cold. But region 2 is really important to be able to identify as the region in which you can separate H2O from C2Cl4. All right, so next week we'll be doing Unit 1, Module 2. So I suggest reading the book. We'll have a pop quiz on either Thursday if you're a Tuesday, Thursday student, or Friday if you're a Monday, Wednesday, Friday student. So I hope this helps. These are all of the ideas and problems that were worked out in the office hours. I suggest coming. You may have different questions. These are the ones that were asked by the students. All right, thank you, and good luck.